Thank you very much, Patrick. I'd just like to say thank you very much for having us here. It's been a fascinating couple of days. I've really enjoyed myself. I've learned a great deal, and also thank you very much for putting up with my bad German, my non-existent French, and my even worse English. We haven't yet spoken Japanese, but that will come. So today I'd like, if I may, to talk to you about the physics of ventilation of the stressed lung. And as Professor Schoettker said, I'm not a clinician. I don't really know how the world works. You, because you're clinicians, do know how things actually go. And furthermore, unlike me as a physicist, you're able to interact with people. But I'm a nerd, a person who is always like this. I do have some conflicts of interest to declare. There they are. And also, as Professor Schoettker said, I'm not a clinician. I'm a physicist. I'm the wrong kind of doctor. I do have warm hands, but that is as far as it goes. And also, the other thing which I should perhaps tell you is that I've only been doing this work in physiology, ventilation, lung mechanics, and so on since about 2015. And when I started in 2015, I knew nothing about this. Optics, okay. Nuclear reactors, maybe okay. But physiology, absolutely nothing. I was a baby. And in this journey, you can see now I've become a rather puzzled teenager with looking like this and, of course, wearing a mask. During this journey, I'd like to acknowledge the help that I've been given by my friend and colleague, Dr. Enck, Professor Enck. Professor Enck is really the inventor, the discoverer of the ventilation techniques that I'm going to be talking about a little bit. And all I did was do the sums on that. So if you want to really know how it works from a clinical point of view, you must speak to Professor Enck, and you will have the opportunity to do that. And this is the program for my talk today. I'm going to just have a bit of a recap of ventilation. You may find it boring, I hope not, but I'd like to show you how we physicists think of a ventilator. And you're probably going to say it's wrong. It is a bit wrong, but anyway, I hope you'll find it interesting. Then I'm going to talk about damage. I'm going to talk about stress, energy. I'm going to talk about how we might limit damage when we're ventilating a patient. And then I'm going to talk a little bit about actually doing it, because we can actually do that. And this is the problem. This is the problem that if you are a clinician in the intensive care unit, you probably face every day. You've got a patient. They're on a ventilator. If you don't ventilate them hard enough, they'll die because they don't get oxygenated enough. They become hypercapnic. If you do ventilate them enough, they probably won't die immediately, but they are at great risk of having lung damage, and the lung damage will kill them. And so you're going along this tightrope like this all the time, trying to balance those two things. And it's a terrible, terrible situation to be in. I don't know how you do it. I couldn't do it, but particularly, for example, during COVID, I have to say, you all did a fantastic job for which actually, the whole world should be tremendously grateful. So thank you very much indeed for doing it. And the problem is that once the lung starts to become damaged, it's even more likely to become damaged. And so you get into this loop. A bit of damage, more likely to be damaged, more damage occurs. That extra damage makes the lung more likely to be damaged. And so you go round and round and round and round like this. The patient's lungs gradually get destroyed. And the big question for me is, actually, what can physics tell us about avoiding that? So here is a ventilator from a physicist's point of view. And a ventilator consists essentially of a pump here that provides the pressure, a patient, obviously, and a vent. A vent is just a valve that is shut some of the time, and then during the expiration phase, the valve lets go. Let's just have a look at some of those components. Here they are. So here we've got a pump. In pressure-controlled ventilation, that pump just provides a constant pressure to the patient. In volume-controlled ventilation, over here, the pump is more sophisticated. It provides a constant flow, so it's blowing constantly into the patient during the inspiration phase. And then when expiration happens, this component here, which is the vent, that vent opens and the gas comes out of the patient, and it comes out of the patient, it's driven out of the patient by the elasticity of the chest and the thoracic muscles. You all know this, it's really rather easy stuff. So here is the ventilation system again, just to remind you, and here is how it works. And these graphs show how it works in pressure-controlled ventilation. Just to point out some of the graphs, up here we've got the pressure, that's the pressure from the pump, and the pressure that the vent lets the lungs down to. Here we've got the flow, and here we've got the lung volume. And this is a pressure volume loop, a PV loop. I imagine you're rather familiar with PV loops. You've all seen them before. I hope so, because these are very important for what we're going to talk about. And this PV loop, for this PV loop, we're measuring the pressure just here at the Y piece. And here in this PV loop, which looks differently, we're measuring the pressure inside the patient trachea. And though you can see those PV loops look different, and they look different because of this. Look, every time the pressure changes, we get a burst of flow going into the patient. So in pressure-controlled ventilation, when the pump comes on, the flow goes whomp, like that into the patient. And the flow profile goes very high, 60 litres a minute maybe more, sometimes 80 litres a minute, and then it falls off as the lungs fill. And then the pump stops, the valve opens, the vent valve opens, and in expiration, the patient's lungs drive the gas out. And when they drive the gas out, the flow goes in the other direction. And it doesn't go in the other direction stably, constantly. It goes like this, a big negative flow coming woof out of the patient, and then it stabilizes, and then it gets smaller and smaller and smaller. And those flow peaks, as you will see, are the bad things about ventilation. But before we get there, let's just have a look at energy in a gas. So if I'm trying to compress a gas, I've got to do work. When you pump up your bicycle tire like this, it's hard. It gets harder the higher the pressure in the tire. And we can calculate how much energy you've got to put into compressing that gas. And the energy is given by this equation here, the integral of the pressure times the volume change. Don't worry, there is no exam at the end. You don't need to memorize that formula. All you need to know is that the pressure times the change in volume is how much work we've got to do and how much energy we are putting into that gas. Let's have a look at that in the context of ventilation. So here I've plotted on the right-hand side a couple of pressure volume loops. This is a pressure volume loop for a perfectly elastic lung. It's behaving like a rubber bag. And you can see that as we increase the pressure here, what happens is the lung goes along this line here, and we increase the pressure, and of course the volume increases. And as I increase the pressure from here to here, the energy that I put into the lung is equal to the area of this part of the curve down here. And that's the energy that I'm actually putting into the gas. It's stored in the elastic system of the lung. That's very important. It's stored energy. Because when I let the lung go, when I let the pressure down, that stored energy, or at least some of it, comes back out of the lung, and it's manifest in the motion of the gas coming out of the lung. Okay, so stored energy in the elastic part of the lung parenchyma. The trouble is that as I put that gas into the lung, it has to go through a resistance. It's got to go through the pipes, and it's got to move my chest. And that movement dissipates energy. If you move the chest, you need energy just to move the thing. And what that does is, when you pump the lung up, actually, it doesn't go along this line here. It actually goes along this line here. And you can see that that line is displaced to the right from the first curve. And when you let the lung down, the energy that you need for the gas to get out of the lung comes down this line here. And the net result is that only part of that energy that you put into compressing the gas and blowing the lung up comes back out. And the other part of the energy, which, by the way, is can be calculated as the area of this loop, that other part of the energy stays inside the lung. And it heats the lung up. And it pulls the tissues apart. And it breaks the collagen fibers. And it does damage. As soon as you start doing damage to the lung, then you find that this PV loop here gets thicker and thicker and thicker. More damage is done to the lung. And let's just have a look at what that looks like. Here is a patient, it's a simulation, but a patient being ventilated. The red is the energy that's being put into the lung. So during inspiration, here comes an inspiration, we're putting that amount of energy into the lung. Then during expiration, the green is the amount of energy that's coming out of the lung, and what's left inside the lung is within that long, thin-shaped area in the middle there. And obviously, if we want to avoid damaging the lung, we'd like to minimize that as much as we possibly can. So what we're doing is, every time we ventilate a patient, we're actually doing work on them. We're dissipating energy inside them. And that energy dissipation, or power dissipation, if we plot the energy as a function of time, is really, really important. And since about 2014, 2015, there have been increasing numbers of papers come out which show that lung damage is related to the amount of power that you dissipate inside the lung. Okay, power is bad. We now need to just think about a couple of other things before we can get onto some of the mechanics. So stress and strain. I'm sorry about the physics here. You don't need to remember the equations, but stress is simply the amount of force that you put on something to stretch it divided by the area over which you're putting the force. So I have to stress this piece of rubber like this. I'm pulling it with force, and I just divide that by the area of the rubber here, and that is the stress. Strain is the amount that the rubber actually moves. The strain is 0, the strain is small, the strain is medium, the strain is big. It's the amount that the rubber moves. And you can plot a graph of stress against strain for a piece of steel. This is the graph over here for a piece of steel. And on the right-hand side here, you can see the same plots for lung tissue, the tissue of rats. Notice how they're very much the same. Here on the left-hand side, we've got this straight line going up here. On the right-hand side, the same thing. The line then curves upwards. On the right-hand side, the same thing. It always also curves upwards. So the lung tissue, in one way, behaves very much like something like steel or any material. In other ways, it's very different, though, because the lung tissue is a very, very complex material. So a piece of steel, when you stretch it, it goes back to where you started. I mean, it's a good thing, isn't it, really, if you think about springs? But lung tissue doesn't do that. And the reason is that lung tissue is this very complex structure. And in simplified terms, I like to think of it like this. There are collagens in the lung tissue. These are strong fibers that run throughout the lung tissue, and they're not very extensible. They provide the strength of the lung tissue. So when you stretch that lung tissue, then what you're doing is you're pulling on the collagen fibers. If the collagen fibers break, the lung tissue will get damaged. There are also fibers of elastin. These are like little coiled springs inside the lung tissue. When you stretch the lung tissue, those coiled springs open out, and they provide the elasticity of the lung tissue that makes it come back. And these fibers are sitting inside a kind of soup, the proteoglycans, a kind of liquid. And that liquid provides viscosity. So the lung tissue is both elastic and also viscous. Let me show you what I mean. I've got some material here. If you have children, this material is the worst material that you can possibly imagine. It's magic putty. You can buy it on Amazon, €5.50. Amazon pays me 10%, by the way, for every one that you buy. Okay, this material, if I stretch it really slowly, as you know, it behaves like a liquid. And the lung tissue is a little bit like this. It's not quite, but a little bit like this. This is behaving exactly as a liquid. And actually, you see how it's stretching and stretching and stretching. Eventually, it'll go all the way down to the floor, providing I move it slowly. But if I don't move it, you see, that's why parents don't like it, because the carpet gets very dirty. Yeah, I see you're nodding. Yeah. If I move it very quickly, just like the lung tissue, the elastic part takes over. And so if I move this quickly, it behaves like a ball. Okay? All right so far? Now, the trouble is, when I move it slowly, I'm putting a small stress on the lung. The force I'm applying is really quite small. When I move it quickly, though, the force gets much higher because of the elastic properties of the material. In fact, for this material, if I move it really quickly, it breaks. It doesn't stretch, it breaks. And it breaks like a crystal. You can pass this around. If you look at the end here, you'll see this is actually like a piece of broken glass. It's not like a piece of putty at all. So this viscoelastic material got some interesting properties. Providing we treat it gently, it won't break. But if we treat it too badly, it will break. It's also got some very other interesting properties as well, which are shown in this equation here. This equation you do have to remember, by the way. There will be a test on this one at the end. No, I'm only joking. But look here, in this integral, it says t minus t dashed. What that integral is saying is that the properties of this material depend on what I did to it in the past. So, if I ventilate the lung quickly, the lung tissue will change as a result of what I've done to it. If I ventilate it slowly, it will change in a different way, depending on what I've done to it. That's really important. You need to remember the properties of lung tissue depend on what you did to it. It's not just a static thing. It changes all the time, depending on what you did to it. And we can actually do more mathematical modelling. I won't go into this, but what I would like to do is to show you another viscoelastic material that you're very familiar with, and that is this material here. This is a piece of rubber out of a bicycle tyre. The net result of the viscoelastic properties is that this material creeps. It creeps. So if you stretch it and let it go, it comes back a little bit, and then later on, it actually creeps back some more. Let me show you how. So this is the rack. This is a piece down here. I've got a piece of bicycle rubber on a spring. And if I extend that out and then let it go, this happens. So here it's stretched. I let it go, it's slack, and you see it creeping, and gradually the tension comes back in the spring, in the rubber. And also, if I stretch it out, and you'll see how it's creeping. It's gradually stretching more and more and more and more and more when I actually apply the spring pressure to it. And lung tissue is very, very similar to that. Okay, so now we've been talking about energy dissipation. And if I say to you, well, dissipating energy in this kind of viscoelastic material can break it, you'll say to me, no, can't be. The material will flow, it will heal itself. Well, let me show you that that's not actually the case. Here is an example of a viscoelastic material that actually does break when it is stretched cyclically, when it's stretched over and over again. So on the left here, we've got a road. On the top is a road in Switzerland, and on the bottom is a road in England. Okay, and you'll notice the road in England is broken. And it's broken despite the fact that the asphalt on the road is almost a liquid. It's broken because the traffic has gone over it over and over again, and the road has been moving like this. Stand next to the traffic lights when a heavy lorry goes by, and you'll actually see the road moving up and down very slightly. And that movement dissipates energy in the asphalt, and eventually that energy breaks the asphalt. And this young gentleman here at the Technical University of Wien did some fantastic work stretching bits of asphalt over and over again, and he found that actually the asphalt did break. And look here, this is a graph of basically how much energy he put into the stretching on each cycle and how many cycles he was able to go before the material broke. And the less energy he puts in, okay, the more cycles it will go. And the more energy he puts in, the fewer stretching cycles it will go before it breaks. Let me show you that that really does happen. We can do it here. I mean, not with the, I'm not going to do this. No, I've got this piece of rubber here. I need a volunteer from the audience. Yeah, Professor Schoettker, would you mind doing? Could you help? Okay. So here's a piece of bicycle rubber. Okay, I'd just like you to tell me, does that feel coolish, warmish?
Comfortable.
Yeah, comfortable. Okay, right. So don't go. I still need you. Okay. Now I'm going to actually dissipate some energy in this. Now, try. Is it warmer?
Warm. Oh,
yeah, it's warm. It's warmer. Okay, and if I really dissipate a lot of energy, oh, it broke. It didn't break because I stretched it a long way. It broke because I was doing many, many cycles, and each cycle dissipated a bit of energy. And if you look very closely here, you can see it a little bit. If you look closely at the crack, you'll find there are tiny, tiny little cracks inside the rubber. And each time I stretch it, another one of those cracks comes because of the dissipated energy. And eventually, all of that dissipated energy that's been gone into this piece of rubber actually shatters the rubber, even though it's a viscoelastic material. So, dissipated energy will break a viscoelastic material. Dissipated energy will break the lung. Need to avoid it if we can. But I'm sorry to tell you, things get worse. This is an airliner that you won't remember it, but I do. It fell out of the sky in the 1950s because of metal fatigue. And in metal fatigue, what happens is you get a tiny crack in the material, and the stress is concentrated around the crack in the material, like this. I've got an example here. Here's a piece of perspex. I'll pass this around, but you'll see I've made a line, a crack inside the material. And I'm going to show you that the stress in this material is concentrated very strongly at the ends of this crack. Do pass it around. Could I have it back when you finish, though, please? Okay. So we can do that by putting that piece of material inside a thing called a polariscope. It's perspex. When I stress the material, the polarization of light going through the material is changed. And here is an experiment which I'm doing in my garage. I've got this sample in a vise. I'm going, and see the stress building up in the corners of the crack? Yeah. Where's the damage going to occur in that material? Where's it going to break first, do you think? Well, it's obvious, isn't it? It's going to break in the corners where the stress is concentrated. And you don't need much energy. Because that stress is concentrated so much in the corners, if you have a lung which is inhomogeneous, stress will be concentrated in the inhomogeneous parts of the lung, then you don't need much energy to do really quite catastrophic damage. And so we get into that cycle I mentioned before. A bit of damage occurs. That damage concentrates the stress as the patient is breathing. That stress concentrates the energy. The energy does more damage. The lung is more susceptible to damage occurring. The stress is concentrated more. More energy is dissipated in the concentrated parts of the lung. The lung gets more damaged. And you can see how we go round and round and round and round and round. And no matter what you do, once that cycle starts, it's really, really hard to stop it, because you've then got to reduce the amount of energy that you're dissipating in the lung to way below what it was originally, so that the lung gets a chance to heal. And if you don't do that, the lung will not heal. It'll just carry on getting worse and worse and worse. So the message for ventilators, people who do ventilation, the message is, 1, minimize the energy dissipation in the lung. 2, minimize the concentration of stress. So let's just talk about energy dissipation. The thing that causes that energy to be dissipated in the lung is partially how far you stretch it, but even more, how much flow is going into the lung. If you put a lot of flow into the lung, you're going to actually dissipate a lot of energy and damage the lung. On the other hand, if you have a little bit of flow going into the lung, then the energy is, you can see, it's obviously a lot less. The thing that concentrates the stress, of course, is inhomogeneity in the lung. We'll come back to that in a minute. So let's just have a look at this here. What I've got here is conventional ventilation. And here on the right-hand side, we've got the pressure at the top. We've got the flow in the middle in green. And then in red, I've plotted the power, the energy per unit time that's dissipated in the lung. And notice how every time you get a burst of flow, you get the power, a burst of power dissipated in the lung. And that power is what's damaging the lung. At the top, we've got pressure control ventilation. That means we get a burst of power doing inspiration, and then things calm down. And then another burst of power doing expiration, and things calm down. At the bottom, I've got volume control ventilation. In volume control ventilation, we've got constant flow on inspiration, then a very strong flow on expiration. So actually, in volume controlled ventilation, we just get one power burst at the beginning of the expiratory cycle. But you can see these power peaks are really quite high. And if you think about it, if you want to minimize the energy that's dissipated in the lung, then actually what you would do is you'd keep the flow constant. You'd actually ventilate going constantly in and constantly out and constantly in and constantly out. And then you would not get these power peaks in ventilation. So here is just a slide which shows those power peaks, 2 peaks per cycle on pressure controlled ventilation, 1 peak per cycle on volume control ventilation. Let's look what happens if you ventilate with constant flow. Of course, as physicists, we can calculate this, and the patients don't mind, which is good. Okay, so here we are. Here we're ventilating a patient using constant flow. Look at the green line. There are no bursts of flow. There's just a constant flow going in and a constant flow coming out. Look at the red line. There are no power peaks. So if you want to minimize the energy that you are dissipating in the lung and the lung damage that occurs from that energy, what you should do is to have a constant flow going in and a constant flow coming out. These equations actually demonstrate that. I've got something, though, that actually demonstrates that maybe a little better. Here we've got a frog on a bicycle. The frog wants to get to the wedding of this young lady here because he doesn't want the person. He's got 2 kilometers to go and he's got 6 minutes to get there. Okay, what's the best way for the frog to reach the young lady? Well, if you're clever, you'll do what my wife does. You'll do this. You'll get on your bicycle and you'll travel at a constant 20 kilometers an hour to get to the young lady. And when you do that, in the first kilometer, you'll dissipate 54 kilojoules of energy. This is about right, actually. It's about what you dissipate on a bike. And in the second kilometer, you'd also dissipate 54 joules of energy. And remember, if you want to make your bicycle go quicker, you've got to press harder. You've got to apply more force, and you've got to dissipate a lot more energy to make the bike go quicker. If you're me, an old man, you say, plenty of time. I can go slowly. So you might travel the first kilometre, not at 20 kilometres an hour, but 15 kilometres an hour. It's great, it's fantastic, because instead of dissipating 300 watts of energy, 300 watts of power, I can get away with 187 watts of power, and the energy that I dissipate is 45 kilojoules. But it takes me 4 seconds to do the first kilometre. So now, if I want to reach this young lady in the 6 minutes, it takes me 4 minutes to do the first kilometre. So if I want to reach the young lady in 6 minutes, I've now got to do the second kilometre in 2 minutes. And if I do the second kilometre in 2 minutes, I've got to press really hard on my bicycle pedals and dissipate a lot more energy. I've actually got to convert myself to this. This is not me. Okay, I can't do this. And actually, the amount of power that I have to dissipate is now not 200 watts, not 300 watts, which is what my clever wife actually used. I've now got to use 750 watts as I go through that last kilometre. And the amount of energy that I use is 90 kilojoules. And so the total amount of energy that I use now is not 108 kilojoules, but it's 135 kilojoules, because I've had to go so much faster in the second part. So let's just compare those. Here we are, my wife, constant speed, 108 kilojoules. Me, I go slowly to start. Oh, it's getting late. Now I have to dissipate 135 kilojoules. It doesn't matter whether I go fast to start with and then slow to finish, or the other way around. If I vary my speed during that journey, I will use more energy than if I go at a constant speed. When you're driving your car, try and drive at constant speed, except, of course, at red lights. Okay, the same thing is true of ventilation. Let's have a look at ventilation loops for the different modes. At the top left, pressure-controlled ventilation. The flow is varying all the time. Great big flow pulses. Look at the loop, it's quite wide. The red part is quite wide. Down on the bottom left here, volume control ventilation. The loop is a bit smaller. On the top right, flow control ventilation. Look, the size of the loop, the area of the loop is about half, actually it's less than half, of what you have in pressure control ventilation, which just goes to show that if you ventilate using constant flow, if you control the expiration, then you will do less damage. And we had some early indications of this. If forgive me, the markers, they're German, but this is an experiment done in Freiburg, and they controlled the expiratory flow slightly, not completely. It's very, very imperfect. But even so, they found less inflammation in the lungs of their pigs by controlling the flow. And I'll show you more in a minute that shows that. But it's not just that you dissipate the energy less, it's actually also, if you have constant flow going into the lung, a low flow, and constant flow coming back out of the lung, then the fast parts of the lung have got time to equilibrate with the slow parts of the lung during that ventilation. You understand what I mean? And what that does is, it means that the fast parts of the lung and the slow parts of the lung more or less expand together. But in pressure control ventilation, they won't. In pressure control ventilation, the fast part goes first, and then the slow part, and then it goes like this. So you can see that between those two parts, you are always going to have shear stress. And we know that shear stress dissipates energy. And I'd like to demonstrate that to you using this model here. These are not two condoms. I see you laughing. It's not two condoms, okay? It is two lung compartments. Okay, I want you to think of these as lung compartments. These lung compartments are glued together along their septum here. So this is like two compartments of the lung which are coupled with each other. And if I get shear stress in the lung compartment, if I get shear stress in the lung, the condom will move to the side. And if I get shear stress the other way, the condoms will move that way. You can see that, can't you? Because they're going to go like that. So this is actually an interesting experiment to actually show that you can actually demonstrate shear stress. And in this experiment, what I'm going to do is I'm going to connect these two lung compartments up to two valves. And you see on the right-hand side, there are actually two valves for the lung compartment. And I can shut one of them off, and I can make a high resistance to the right-hand lung compartment, which means that its speed will slow down a lot. All right, so far? So I hope that I can demonstrate to you that we're going to get less shear stress if I ventilate these lung compartments with the valve shut. If I use flow control ventilation, constant flow during the inspirator-expiratory cycle. Here is the apparatus on the floor of my kitchen. I couldn't bring the valves. They won't let me on the aeroplane with them. They wonder what they are. It's true. I always get stopped. And you can see we've got two big valves there and a little valve on the right-hand side. That little valve is a high resistance valve. The two big valves, when they're open, are low resistance. And I also made for you a special ventilator. This ventilator is an experimental ventilator, and it will do flow-controlled ventilation with constant flow in and out. It will do pressure-controlled ventilation, a normal pressure-controlled ventilation, high pressure, low pressure, high pressure, low pressure. It will do volume-controlled ventilation, constant flow in, and then low pressure, constant flow in, and then low pressure. You can switch between the modes. Here you can see on the right-hand side the graphs. I'm going to show you these live in a minute. At the top, we've got the pressure. In the middle, we've got the flow. And at the bottom, we've got the volume of the lung. And here, we've got a pressure volume curve, a PV loop. You can already see it's actually a bit different to what you'd expect. Let me show you what happens when we actually ventilate these lung compartments. So it's not starting now. Okay, right, here we go. So I'm ventilating this model. At the moment, both big valves are open, so very low resistance. Ventilating, you look at the flow. The flow is constant, going plus 2 litres a minute, then taking the flow out of the lung, minus 2 litres a minute. The volume goes up and down in this triangle wave, and the pressure goes more or less up or down. And the PV loop is probably unlike anything you've ever seen before. Look, it's actually a thin little PV loop. And because that area is so small, it shows that the energy being dissipated in those lung compartments is very, very low. In fact, I can tell you, it takes about 20 millijoules of energy to blow up a condom. And so next time you want to impress your friends, you can tell them that. Okay. On the right-hand side here is a slider that shows the power. At the moment, we're dissipating 4.8 millijoules in this whole lung system, 4.8 joules a cycle. Now I've altered the resistances so that one condom is slow and one is fast. I've increased the overall resistance in the lung. Look at the loop. The loop gets a little bit thicker, and look how the condoms move. Even though we've got lung compartments of different resistances here, the condoms are actually moving together because they've got time. The slow one has got time to catch up with the fast one. You can see it moves sideways just very slightly, but only a little bit. And look, the energy dissipation, it's gone up a little bit. It's gone up to 8 millijoules per cycle. Gone up to 8 millijoules per cycle. But actually, I promise you, it's not very much. This patient is probably going to be okay because the energy dissipation is really, really small. Okay, now, in a moment, I'm actually going to switch. Here, I'm now switched to pressure control ventilation. Exactly the same conditions, exactly the same upper and lower pressures, exactly the same volume in the lung. And look at the loop. The loop gets much thicker. And under pressure control ventilation, this same lung system needs much more energy to make it go. And look how the condoms move. There. You see it twitch sideways? That was expiration. Inspiration. See it twitch sideways? And the lung isn't very happy, is it? They're going every time. You can see high energy dissipation. Look at the loop. Look, the energy is up to 35 millijoules per cycle. It was 8. It's gone up to 35. It's gone up by 4 times for this system, just because we're ventilating with pressure control ventilation rather than with flow control ventilation. Okay, now we're ventilating with volume control ventilation, and you're going to get a classic volume control ventilation PV loop. And for this particular lung, actually there's even more energy dissipated. And you'll notice that actually we get the twitching of the lung just on expiration only, not on inspiration. And as I say, we get even more energy dissipation. It's going to be about 50 millijoules. But there are some additional advantages of doing that. If you've got a flow which is varying in the lung all the time, you never know where it is. You remember I said to you that what happens to the lung depends on what you did to it before, and the harder you hit it, the more it changes in time. Not just that, all the measurements become much harder. If you've got constant flow, the measurements become very, very easy to do. And so then you've got the opportunity to actually optimize the ventilation of the lung. Here is a pig being ventilated using flow-controlled ventilation. On the left-hand side, the pressure is going from 0 up to about 25 millibars. And look, this curve, this PV loop, now traces out a classic lung compliance curve. You can see the upper inflection point, the lower inflection point in the PV loop. And if you optimize the ventilation, you reduce the driving pressure, the PV loop becomes straight, you're minimizing the energy, and you're getting an additional advantage by using flow control ventilation in terms of energy dissipation. Not just that, you're getting an additional advantage in terms of gas exchange as well, because the lung is more homogeneous, as I showed you with those two condoms. So here are some examples from colleagues in Innsbruck, and the thing I'd like to point out to you is look at the mechanical power, first thing. So in PCV, to ventilate this pig, we needed 22 joules per minute to ventilate the pig. In the flow control ventilation, for the same gas exchange, look at the carbon dioxide. The carbon dioxide is about the same gas exchange. We only needed 5.8 joules per minute, less than half. And look at the minute volume. For PCV, we needed 12.7 litres a minute to keep the carbon dioxide down. And even then, the carbon dioxide is a bit high, you'll agree, 45 millimetres of mercury. Under FCV, flow control ventilation, not only are we damaging the lung less, but we need less than half of the minute volume that we needed for PCV to keep the carbon dioxide down. So, very, very interesting. Now you might say, well, look, Tom, you know, it's all very well you physicists talking about Schrödinger's equation and E equals mc squared and all this. It doesn't really apply in practice, but actually it does. This paper has just come out, actually, in the European Journal of Anesthesia. It's a retrospective study of ventilation, looking at the association between mechanical power and mortality after 28 days in the intensive care unit. And this graph, you can see we've got mechanical power along the horizontal axis, and we've got the hazard ratio for death on the vertical axis. And look, the hazard ratio increases. It's strongly correlated with the amount of mechanical power. And the interesting thing is that these patients were not ARDS patients. They were like you and me. They had healthy lungs. And even so, the mechanical power was enough to actually damage the lungs and cause them to die at the end of 28 days. So what I'd like to say to you is, if you ventilate me, please, please, please keep the mechanical power down. Okay, I'll take questions in a minute if that's all right. So if you want to minimize harm, as a physicist, and I'm only a physicist, I can't recommend things clinically, please control the flow throughout the ventilation cycle, and it has all of these benefits: minimizes dissipated energy, maximizes homogeneity, etc., etc., etc. And I have a little prayer for you. So, first of all, may your flow remain constant, and therefore your lungs homogeneous, and therefore your wasted energy and your stress minimized. Thank you very much.